In this lesson, we're going to look at horizontal and vertical stretches, compressions, and reflections. So in the last lesson, we looked at horizontal translations of parent functions, horizontal and vertical translations. So by the end of the section, you should definitely be able to graph those translations, and you should also be able to graph functions with stretches, compressions, and reflections to the parent functions we've looked at. You should be able to name them properly. And if you were given the transformations, you should be able to come up with the equation. So this one's sort of working backwards. So in the last lesson, we started by transforming the quadratic function because we were familiar with it. Now we're going to start by graphing the square root function because that's going to be easier to see reflections with. So we're going to start with vertical stretches and compressions. So log on to Desmos and graph these four functions and sketch them quickly in the graph here and then come back to the video. So once you have it your graph should look something like this. So let's quickly go ahead and label it. So we have this red guy in the middle. That was the graph, that was our original parent graph. That's y equals the square root of x. So that was this one over here. And then we have this one that was stretched upwards. That was the graph of y equals 2 root x. So that was this one over here. Next we have this green graph over here. And this was the graph of y equals a half times the square root of x. And then we have our final graph at the bottom, and that was the negative graph. I'm just going to use blue here again. And this was the graph of y is equal to negative 2 root of x. And I'll maybe just use a squiggly line. I'm going to put a squiggly line under here. And this one was black. So let's start looking at some patterns here. So remember, we're going to always compare it to our parent graph, which is right here, f of x equals the square root of x. So if I take a look at this blue graph here, I can see that in the actual equation, a 2 was being multiplied outside of the function. So in the last lesson, we were looking at when numbers were being added or subtracted. So it would have looked something like this, square root of x plus 2. So again, this 2 is outside the function. Every single y value was increasing by 2, and so it was going up. Now, instead, we have 2's being multiplied against the function. So now we're going to be multiplying the y values, and look what it did. What it did is it brought all of the y values up. So we call that a stretch. So all the y values are being stretched from their original place upwards. Let's take a look at the green graph here. So it looks like it's been shrunk compared to our original parent graph. So if I go back and take a look at the equation, I see what was multiplied by it was a fraction. And anytime you're multiplying something by a fraction, the number gets smaller. So for example, 2 times a half becomes 1, and 1 times a half becomes 0.5. So what's happened here is, again, we're doing something outside of the function. So it's this case it's multiplying against the y values. And what it's doing is it's shrinking them. The y values are going from up here to down here and up here to down here. So when we multiplied by a number that was bigger than 1, it stretched them. The y values got increased. When we multiplied our function by a number that was less than 1, the function shrank or compressed. All the y values became lower. And on top of that, we have this orange or yellowish graph that completely flipped over. So it actually looks like the blue graph just reflected in the x-axis. So it's been reflected in the x-axis here. And if you take a look at the equations between the blue graph and the orange graph, they're this graph here and this graph here. They have the exact same absolute value or number. The only difference is that there is a negative here. So we can conclude from this that this absolute value of this number, so this number 2, that's what's going to affect how stretched it is or compressed it is. And this negative that's being multiplied outside of the function, that's going to affect its reflection in the x-axis. So now we're ready to draw some conclusions. We're going to call anytime we multiply a number outside of a function, we're going to refer to that number as the letter A. And that's similar to what you may have used in grade 10. If it's not, remember the letter actually doesn't matter. You can use whatever letter you want. So when this A is greater than 0, there's no reflection. And we saw that in these examples here. All three of these have an A value that's positive. Here A is a half, here A is 2, and here A is 1. And all three of these graphs have no reflection at all. However, when we have a negative A, that's when we have a reflection in the x-axis. So when A is less than 1, we have a reflection in the x-axis. So now let's look at the absolute value of A. So we're just looking for the actual number. Remember, the negative, that just affects the reflection. So when the absolute value of A was greater than 1, so whatever we're multiplying the function by was greater than 1, the function was vertically stretched. And we say vertically stretched, but because since this number is outside the function, it's affecting all the y coordinates. Just like when we added a number outside of the function, what we did is we added whatever this number was or subtracted to the y coordinates. So when we are dealing with numbers that are multiplying or adding and subtracting outside of the function, we're affecting the y coordinates, which is why it's a vertical stretch. Now when the number we're multiplying by x is less than 1, that's when the graph shrank and it became vertically compressed. And that's because we were multiplying all the y values against outside the function by a number that was less than 1, which means it was going to decrease. So if you're still not sure about these patterns, I highly recommend for you to click on one of the Desmos activities that have been set up for you on Google Classroom and play around with those sliders and take a look at specifically A and see what it does to each of those functions. Let's take a look at now horizontal stretches and compressions. So if you haven't done so already, take a look at these functions, punch them into Desmos, and quickly sketch them onto the graph here and come back to the video. Once you've graphed them, they should look something like this. So what we're going to do is we're going to quickly label them. So our original parent function, that's again in red here. So we're just going to label it that this one here was the graph of y equals the square root of x. When you graphed this guy over here, you got this blue graph right here. So let's label this guy. This was y equals square root of 2x. So that was this one. That was the red guy. And when you graphed this guy here, where you're multiplying the x's by, or this x variable by a half, we got this green graph over here. So we'll label that one. This was y equals square root of a half x. And then finally, when we graphed this one that had a negative outside of this, a negative inside the square root, we got this reflected function over here. Y equals square root of negative 2x. And we'll just use the squiggly line again. We've got a squiggly line here. So if you compare these graphs to what we looked at when we were graphing vertical stretches and compressions, it kind of looks like something similar is happening. When there's a number that was greater than 1 that was multiplying against this x value here, it looked like the graph got bigger, got stretched. And the same thing when we were multiplying this x variable by a number that was less than 1, it looked like it shrank, it got compressed. Even though it looks the same, these graphs are actually different. So even though this here looks like it's been stretched, it's actually been compressed. And the reason is, we remember when we were doing translations, whenever we took our original parent function, we did something inside that function. So let's say that we added 2. We knew that this affected the x coordinate, not the y coordinate, if it was inside the function. We know it was really what we originally did to the x coordinate was opposite of what we see here. So really every x coordinate was subtracted by 2. Looking up here now, we can see that there's a number being multiplied against the x directly. So this is also affecting the x coordinate. Meanwhile, over here, the 2 was outside of the function, therefore is affecting the y coordinate. So it's a y coordinate, and this is affecting the x coordinate. So here, the x coordinates are changing. So let's track the x coordinates. So let's track it between the red graph and the blue graph. So we're going to compare red and blue. So let's take a look at this algebraically. What actually happened to this x? We already have our equations isolated for y here. So when a number is affecting the y, we can easily see what it must have done to the y coordinate. So here it multiplied the y coordinates by 2. Now let's take a look at if we want to know what happened to the x coordinates, we're going to have to do a little bit of algebraic manipulation. So I'm going to rewrite this as our y. So y is equal to 2x. So I've changed it from sort of function notation to y. Now I want to isolate for x and see what happened to this x variable. So to get rid of that square root, we are going to square both sides. So I'm going to square this side and we're going to square this side. So we are left with y squared is equal to, and we're just left with 2x here. And now we're going to keep isolating for x by dividing by 2 and dividing by 2. And I'm going to rearrange it so that my x is on one side. So I have x is equal to y squared all over 2. Okay, so that y squared here, that's actually our original function. So if I were to rewrite this guy, it would be y is equal to square root of x, and that's going to be equivalent to saying that x is equal to y squared. So that's where the y squared came from. So if we compared the original function to this function, we can see every single x value was divided by 2. So that's what's happening here. Every single x value gets divided by 2. So if I were to take a look at this red and compare it to the blue, let's track the x values. So I'm going to take a look at this point here. This point here is the point 9,3. So the square root of 9 is 3. And if this x value was divided by 2, well, half of 9 is 4.5. So if I take a look on this blue graph here at 4.5, that's about here, we can see that the y value is unchanged. The y value is still 3. So what's happening, if you can follow, is that all of the x values are being cut in half and the y values are not changing. Over here, we found that when there was a number multiplying against our function, all the x values remained unchanged and the y values got multiplied by 2. So just like when we were working with translations, whatever is happening to the x is actually opposite of how it looks, but because we know that we need, in order to really see what's happening to those x coordinates, we need to rearrange it so that the equation is in terms of x. So this looks like the x's are being multiplied by 2, but actually they're being divided by 2. So all of the x coordinates are being cut in half and the y coordinates are staying the same. Take a look at this guy right over here. All the x coordinates look like they're being multiplied by a half. However, if we rearrange it, it's going to be opposite of that. Instead of being multiplied by a half, they're going to be divided by a half, which is the same thing as multiplying by 2. I'll show you very quickly. We have our equation, y is equal to the square root of 1 over 2x, which is going to translate to y squared is equal to 1 over 2x. If I want to get rid of that 2, I'm going to multiply, or 1/2, I'm going to multiply by 2 on both sides. And I'll be left with 2y squared is equal to x. Another way to write that is x is equal to 2y squared. I was able to do that because a half times 2 is going to equal 1, which is where that 1 came from. So if I take a look at our function that we started with and what we realize is actually happening to our x coordinates, all of our x coordinates are getting multiplied by 2. Here it looks like they're getting multiplied by a half. They're actually getting divided by a half, which is the same as multiplying by 2. So if we track it on our graph here, in this graph here, all the x's are actually getting multiplied by 2. So let's track the point at 4, 2, which is right here. And for the green graph, if our x are getting multiplied by 2, that 4 is going to become 8, which it is, and the y value is still going to remain 2. So if all this is highly confusing, you can always just use the summary at the bottom, which we're going to do in a second. One last thing I want to point out is the only time that the graph flipped over the y-axis when there was a negative here. So all those x values are getting multiplied by -1. But actually what's really happening is all the x values are getting divided by -1, which is the exact same thing as being multiplied by -1 anyways. So the x values that were here now are over here. So the x value that was +5 is now -5. That's why we have a reflection in the y-axis. Also note that just like for vertical stretches and compressions, the actual stretch and compression is not affected by the negative value. So this blue graph and this orangey yellow graph, they have the exact same stretch. And take a look at their equations. This one is y equals square root of 2x, and this one is just square root of -2x. The only difference between them, they have the exact same absolute value of the number that's multiplying against x. The only difference is the negative. So let's summarize everything below. So we're going to use any number that's getting multiplied or divided against the x. We're going to use the letter k. So when k was positive, there was no reflection. So we can all agree upon that. It doesn't matter how confused you are at this point. So all of these equations here, all of the the values in front of x are positive, and therefore there's no reflection. And when there was a negative in front of that x, that's when we had a reflection. So let's just finish this up here. So when this value of k is less than 1, so it's negative, the function was reflected this time on the y-axis. So now let's talk about the absolute value of k. So when this actually has a number that's greater than 1, then we got to go back and take a look at what actually happened to the graph. So some students might say, oh, well, it got stretched, but we're talking about the horizontal. These k affects the x coordinate. And so we got to look compared to this red graph, what happened to the blue graph? Well, all those x values actually shrunk. They got smaller. So this is called a horizontal compression. So let's fill that in below. So when our k value is greater than 1, the function is horizontally compressed. Okay, and the last conclusion is what happens when that number that we're multiplying x by is less than 1. And we're talking about the absolute value of it. Well, if we take a look back up here, that was this example down here where we had a number that was less than 1 being multiplied by x. What happened was when we tracked the 0.42, the 4 became an 8. All the x values got multiplied by 2, and so it horizontally stretched. So let's write that down here. So when absolute value k is less than 1, the function is horizontally stretched. So here we have a summary of all the transformations we just talked about. So we looked at when we're multiplying a number outside the function and when we're multiplying a number inside the function. And we know that anything we're doing outside the function is going to affect the y coordinate. So I'm just going to write a little reminder, y coordinate. And anything that's happening inside the function is going to affect the x coordinate. So the y coordinate, because we already have our equations isolated for y, is very straightforward. The x coordinate is a little bit more backwards, and we know the reasoning for that. So just in general, when this a is greater than 0, there's no reflection at all. Same with when k is greater than 0, there's no reflection. But if a is less than 0, there's a reflection in the x-axis. The reason is because all the y's are going to go from positive to negative or negative to positive, vice versa. And when k is less than 0, so it's negative, it's going to be reflected in the y-axis. So now let's take a look at what if this number is greater or smaller than 1. Well, if our a value is greater than 1, then it's going to do exactly what it looks like. It's going to multiply all of the y values by a. So we say that this is a vertical stretch by a factor of a. A is what we're multiplying all the y values by. Let's take a look at when k is greater than 0, it would look, greater than 1, it would look like it's being, that number would be multiplied by all the x's, but actually it's the opposite. All of the x's are going to be divided by that k. So we say that the function is horizontally compressed by a factor of 1 over k. That means instead of multiplying by k, we're dividing by k, which is the exact same thing as multiplying by 1 over k. Here's what I mean. Let's say our example of our function was, let's go back to the square root function, was y equals 2 times x. We know if we rearrange this thing that actually what's happening to the x is it's getting divided by 2. So I would take my x coordinate and divide it by 2. But isn't that the exact same thing as if I were to take my x coordinate and multiply it by a half? So there's my k value right here, the 2. So I'm dividing all the x coordinates by 2. Another way to think about it is we're multiplying all the x coordinates by 1 over that, which is here. And that's why we say it's horizontally compressed by a factor of 1 over k. So the last note is when our numbers inside or outside the function are less than 1 but greater than 0. So the absolute value is less than 1. In this case, for a, the function will be vertically compressed because we're multiplying by a number that's smaller than 1. And for the x coordinate, you can guess that that's going to be the opposite. In this case, the function is going to be horizontally stretched by a factor of 1 over k. So we're going to make one note about graphing. So if it wasn't clear, in order to graph a, so in order to change the points based on this a value, we are going to multiply all the y values by a. Multiply y coordinates by this a value. And to graph k, or change the points based on this k value, we are going to divide the x coordinate by whatever this k value is. Okay, so using the summary above, let's take a look at each of these functions here that have vertical and horizontal stretches and compressions. And let's name each of the transformation and describe how we would actually graph the following functions. So what we can do is, we're going to list out the transformations, and then what we're going to do is we're going to make our t-chart, and we'll determine what are we going to do to the x coordinates and what are we going to do to the y coordinates. So feel free to continue to flip up here to be able to check those rules. And remember, we're going to continue with what we learned in the previous lesson about horizontal and vertical translations. So here's a reminder of what the general function notation with all the different transformations would look like. So we know what our A does, it's vertically stretches, compresses, and reflects. We know what our K does, horizontally does that. D is our horizontal translation, and C is our vertical translation. So with this first guy here, of course, we have to list our parent graph. So if you can take a look, we have a clue here. We've got a cubed, which means that the parent graph is the cubic function. So our parent graph is the cubic function. So f at x equal the cube, not the cubed root, x to the power of 3. Okay, so our parent function is cubic function. So now let's go one by one and start naming these guys. So this one here, what letter is this? Well, it's outside the function because it's not being cubed. So this must be a. Our a is less than 1. The absolute value of a is less than 1, which means that this is going to make all the y values smaller. So if you use the summary above, this is going to be a vertical compression. And we say by a factor of 1/3. And that's because we're going to multiply all those y values by 1/3. So let's keep on going now. Now we have this negative. It's inside the cube. So it's inside this function, which means it's affecting our x coordinate. And it's multiplying against x, which means it must be k. So this guy in here is our k value. So that k value is actually -1. So if you look above, -1 is neither or the absolute value of -1 is neither greater than 1 or less than 1, it's equal to 1. So there's going to be no stretch or compression, but because it's negative, there is going to be a reflection, and it's going to be in the y-axis. Reflection in the y-axis. All right, so we don't have a D value, we don't have any horizontal shifts, but we do here have a C value, a vertical shift. So this guy is outside of the function, it's outside of the cubed, so it must be C. So if we use our summary from the previous lesson, we know that there's going to be a vertical shift or translation down 1. Alrighty, so here's the list of transformations. We know our parent function. Let's summarize everything in a T-chart where what would we do to the x-coordinate and what would we do to the y-coordinate. So we're going to start off with x here, and we'll start off with y here. We're going to go transformation by transformation, what would happen. So let's start with the first guy, our a value. We know that these numbers outside of the function are always going to affect the y-coordinate. So our a, this is going to get multiplied by the y-coordinate. So I'm going to put a 1/3 being multiplied by our y. Next, we have this -1 that's getting multiplied by our x. That's our k value, so we know it's going to affect our x coordinates inside the function. So it looks like it's getting multiplied by x, but we know it's actually getting, x is being divided by -1. In this case, multiplying by -1 and dividing by -1, it's really going to do the same thing. But we know that's truly division there. Okay, and then we're moving outside of the function again, so we have our C, that's going to affect our y-coordinate, and everything is getting shifted down 1, which means that we are going to take 1 away from the y-coordinate, and that is our sort of key that we are going to use to transform all the points of the cubic function to our new transform function. Okay, let's take a look at this function here. It has a fraction in it where our x value is at the bottom, so these are some hints to let us know that our parent function must be the reciprocal function. F at x is equal to 1/x. And now we've got to sort of decode what each of these letters are. So the 4, maybe you're not sure what that 4 is, but the 2, that's inside the function right beside the x, so that must be our D value. So I'm just going to make a little label that guy must be D. And now we got to figure out what this guy is. Well, I'm going to rewrite this as, let's erase, oh, never mind. Okay, so I'm going to rewrite this as, I'm going to bring the 4 out, and I'm going to list it as 1/x plus 2. If I bring the 4 out here, remember if I were to bring it in, it would just be 4/x plus 2, so I would get this back again. So if I bring the 4 out, it's easier to see that here's my original function, it's getting multiplied by 4. So this 4 is actually our a value. So if that's our a value, because our a, absolute value of a is greater than 1, that must mean that there's a vertical stretch by a factor of 4. Okay, now if we move on to our D value here, we know that this is going to be a horizontal shift. And we're going left 2 units. Okay, so now that we've got this done, we have our plan. Let's go ahead and figure out what would happen to the x coordinate, what would happen to the y coordinate. Okay, so let's take a look at this first guy, this 4. We know that it's our a value. It's going to create a vertical stretch, so therefore it's going to affect our y coordinate and it's going to multiply against our y coordinate. Next, we have a horizontal shift left 2 units, which means every single x value is going to be subtracted by 2. And then now we have our key that we can apply to our parent function and graph. Okay, so now let's take a look at our final function. It's sort of laid out nicely because it looks like it sort of mimics what we have in our function notation here. So we see these absolute value signs, so that gives us a hint that our parent function is the absolute value function. So our parent function is f at x equals the absolute value of x. Okay, and because it's laid out so nicely in our absolute value function, we can really easily see which one is A, K, D, and C. So this number is getting multiplied outside of these absolute value sign, so it's outside of the function, so this must be our a value. We have another number being multiplied directly to the x inside the absolute value sign, so inside the function, so it must be our k value. Okay, we have a number being subtracted from our x coordinate, so we know that this must be our d value. And finally, we have a number being added outside those absolute value signs, so outside of the function, and that is our c value. So let's go ahead and use the summary above, use the summary from the previous lesson as well. Let's list out these transformations. So we have this a value. First of all, it's negative, so we know that there's going to be a reflection in the x-axis. Then if we take a look at the absolute value of a, so the absolute value of negative 3 is 3. That's going to get multiplied by all our y values, and there's going to be a vertical stretch by a factor of 3. Moving on, we have the k value is a half. It's getting multiplied by x, but really we know what's happening is all the x coordinates are getting divided by 1/2. Which means they're going to get bigger, and so we have a horizontal stretch by a factor of 1 over k, 1 over 1/2, which is going to be 2. Okay, now taking a look at our d, the actual value of d is 5. It looks like we're subtracting 5 from x, but we know we're really adding 5, so we're going to the right. So we have a horizontal shift, right 5. And last but not least, we have this number being added outside the function, so it's affecting our y coordinate, and everything's getting shifted up a third. So we're going to say we have a vertical shift up a third. So let's make our t table. What's happening to the x coordinate? What's happening to the y coordinate? Okay, and let's go through them one by one. Okay, to start off with, we have our a value. Our a value is -1. That's creating a reflection and a vertical stretch. That's going to affect our y coordinate, so I'm going to multiply all the y's by -3. Next, let's take a look at our k value. Our k value, that's going to affect the x coordinate, and it's opposite of how it looks. Instead of multiplying x by 1/2, we're actually dividing x by 1/2. So I'm going to divide x by 1/2. Now that is the exact same as multiplying by 2. So if you prefer to write this just as 2x, that's also accurate. Now let's take a look at our d value. We know that that's being shifted to the right 5, so we're going to add 5 to that remaining x coordinate. And then last but not least, we have our c value. It's being added to the y because it's shifting it up. So we're going to add a third, and we're done.